Let me see. Oh. And we were doing 2,3-butane diol. Why is it not? 2,3-butane diol. And that's why I wrote up the first one up here. OH. I really apologize. It's going to be really sloppy now because I have to use my big old fingers. Because I'm assuming no one has a stylus out there. Just in their back pocket. Okay, and we have a hydrogen. So this was the one that we've already done before, and so that's why I'm just going to redraw it for this part. And then the mirror image for it, which you guys should already have in your notes. OH, H, and so just to review, how many chiral carbons were there in 2,3-butane diol? 2. And so the theoretical maximum number of stereoisomers would have been 4, because it's 2 to the power of 2, since there are 2 chiral carbons. If there were 3, there'd be 2 to the power of 3, which are 8, and so on and so forth. Okay, so this is the second one, because remember we had the mirror going down there. Then we had the third one, which I don't remember which one I had drawn before. It doesn't. Was the one that I had for the third one, were the OHs on the left or the right? The right? Okay. H, and then we have the mirror. That's supposed to be a 3, but I can't. And now they're both on the left. We had already talked about what was the priority, and so just to refresh your mind, we have the OHs are large. The medium was the other carbon, the non-methyl carbon. The small, and we have the extra small. So this one would have been large, small, medium, and extra small. And then we always do what I call the looks is. We already did that for the first one, which I wrote that answer on the board. Okay, it's supposed to be looks and is. So in that first one, the one that was on the left, we had where overall this would be called 2s, 3s butane diol. So if we do the priority here on this one, remember we always go, and I'm going to do the top one first. So we go to large, medium, and small. You just ignore. Does it look like it's an R, or does it look like it's an S? It looks like it's in large, medium, and small. Is it going to the right or to the... Whoops, where am I going? Large, medium, small, yes. Now, the question is it really... Is the extra small group coming out towards us, or is it going away from us? On a Fisher projection, is the horizontal line, because it's on the horizontal line, is coming towards us. So does that mean it really is an S, or is it really an R? What's the rule? It's an R, because it's the opposite of what you think of. Remember, if the extra small group is going away from you, it really is what it is. If it's coming out towards you, it's not. Okay, and so now we do the second one. We have large, medium, small. Does it look like it's an S or an R? Does it look like it's an S or an R? It looks S. And is the extra small group coming out towards us or going away from us? Sorry, say it with some conviction here. Towards us, so it really is R. Okay. I'm just going to write the answers for the other one before. This one was an S. This one was an S, just because it's going to be important later on. You already have it in your notes. Now let's do the bottom one, the one on the left-hand side, the bottom. The priority is still the same. Or Why is it now not wanting to? Large, small, medium, and extra small. Large, small. Now, one thing that you could do is you can still on your own go through and do the swirlies and everything else, or you can kind of do the cheat method, and you could see if we look at this one up here, when the alcohol was on the right hand side, which it is down there, we know that it really is an S. And you can do the method on your own, and it really is. It looks like it's an R, but it really is an S. So I'm just going to write that answer right here. So we know that this one right here is an S. Okay. Whereas if we look, see now we have the alcohol on the right hand side on the bottom, and when the alcohol is on the right hand side of the bottom, it looks like this one. And so it looks like an S, but it really is an R. So I'm just going to write the answer down for that one right here. Likewise, we can now go on this one. The alcohol's on the top left. It looks S, but it really is R. So I'm just going to write the answer down. Oops, I did the exact opposite of what I said I was going to do. Okay, and then we do the same thing for the bottom here. When it's on the bottom right, it looks like this one, and it really is an S. Okay, so I'm just going to go ahead and write the answer. But on your own, if you figured it up, and I suggest these are definitely on the exam tonight, so make sure you've been doing the problems as you go along and understand this in the book. So the question is here, first off, the term that's used for these two are called enantiomers of each other, right? Because they are mirror images that are non-superimposable upon each other. But if we look at compound 1, or I should say isomer 1, stereoisomer 1, and stereoisomer 3, they are still stereoisomers of each other, but they are not enantiomers. So there has to be another term for it. And that term is called diastereomers. So I'm just going to put that, I don't know where I have room for it, but just so that way you can see what I'm saying in case you didn't understand me. Diastereomers. Diastereomers essentially are just stereoisomers that are not enantiomers of each other. Okay? So that's why if we look at, well, I'm calling compound 1 the top left versus the bottom left. Those are diastereomers, but compounds 1 and 2, or isomers 1 and 2, are enantiomers of each other. So now the question is, we've drawn the 4 possible and the 4 theoretical stereoisomers. What's the actual number? Are these down here chiral? The answer is no. And why are they not chiral? These are chiral, right? We have 2 chiral centers there, 2 chiral centers there. Why are these compounds here not chiral? They have that plane of symmetry. You could imagine a guillotine, well, not chopping it in half this time, but folding it, in the top and the bottom half are the same. Okay, and so there's that plane of symmetry in there. So these are actually the same structures. These are identical. Okay, and so and there was a special term for that. Does anyone remember what that term was called? It's a 4-letter word, meso structures. And so that's a mesostructure. So the actual number for 2,3-butane-diol are 3 stereoisomers. We have 2 that are enantiomers of each other, and we have the 1 mesostructure, which is a diastereomer of the other 2. So just because there are times that the theoretical number will not match the actual number, we can actually mathematically figure this out and to prove that. So let's say, for example, I don't know the actual answer, but let's say, for example, that the R rotates light positive, I'll say alpha degrees. Okay? And so if R rotates light positive alpha degrees, how many degrees will S rotate light? Negative alpha. And so if we now just figure up the math here, this would be negative alpha degrees and negative alpha degrees for the one that's on the left, sorry, because the one that's SS. So when we add that up, this compound right here rotates light light negative 2 alpha degrees. So if alpha was 15, it would be negative 30. The one here on the right, it's really RR. So it's going to rotate light positive alpha degrees and positive alpha degrees. So when we add plus alpha and plus alpha, what's the total going to be? Plus 2 alpha degrees. And so, for example, if alpha was 15, then it'd be positive 15 degrees. The other one's positive 30 degrees. The other one was negative 30 degrees. So that's why they truly are enantiomers. Now let's do the math on it, and it doesn't matter which one of these that we pick. I'm going to just pick the one that's on the left. The S was negative alpha degrees. The R was positive alpha degrees. So when you have a negative alpha and a positive alpha, it's 0. So it doesn't rotate light at all. They cancel each other out. So that's why it's a mesostructure. So we proved it mathematically as well. So when can you actually come to expect the possibility of mesostructures? And it's really easy to do this with Fisher projections, like for these sugars and things like that. It's really, really simple. So I'm just going to give you some examples. By the way, this one right here is a reduced sugar. These are only alcohols and hydrogens. It's just the fact that I don't have my stylus, and so it's not picking it up very well. So the one on the left is called a reduced sugar. Isn't that nice? My mama mentioned me in a comment. The one here is the oxidized sugar. It'd be the one that's more naturally occurring. Let's see, 1, 2, 3, 4, 5, 6. Yeah, the one that's more, I should say more naturally occurring, but for lack of a better term, when you take biochemistry, if you take biochemistry, you'll go over this kind of stuff. So you should just be able to, hopefully after I explain it in like 30 seconds, to be able to look at a Fisher projection like this and just come up with an idea off the top, and come up with the answer off the top of your head whether or not a mesostructure is possible. One of these has a possible mesostructure. One of them does not. Which one has the possible mesostructure? The one on the left or the one on the right? The one on the left. Okay, so there are some stereoisomers of it that will be mesostructures. And the easiest way to tell, does anyone know what's the easiest way to tell? Like, how do I know that the one on the right does not have one? The top and the bottom are different. That's why I say, just it's as simple as this. This is an oxidized normal sugar. That's called an aldehyde. The ch4 is really a carbon. It looks like this if you draw it out. It's a carbon. It's got a double bond to an oxygen. It's got a hydrogen hang off of it. But they abbreviate it ch4. Okay, so that's different than the bottom down here, which is just a regular alcohol. One's an aldehyde, one's an alcohol. So there's absolutely no way for there ever to be a mesostructure. The other one, since you do have the same top and bottom, and all of these are alcohols, then you know that there's a possibility. In fact, this one's going to have more than one possible mesostructure just by looking at all of them. You can imagine all the alcohols being on one side. You could have alcohol here, alcohol there, and hydrogen, hydrogen. That would be another plane symmetry within there. And so with the top and the bottom halves would be the same. Now, if just one of these, let's say instead of an alcohol here, that we put in nitrogen with hydrogen hanging off it, which is called an amine, an amino group, then there would be no mesostructure on that one, since there's an even number of carbons. Now, if it was on the odd number of carbon and you put the odd group on, then you can imagine there's still planar symmetry. But the easiest way, first, is just look, don't spend a lot of time, because you're going to have to learn to manage your time wisely on exams, is just look, is the top and the bottom the same, or are they different? Because if they're different, there's absolutely no way. And we can even figure out the theoretical number. I would never ask you to figure out if there's something that's got, oh, here, let's just do an example. Okay. Give everybody a moment to get caught up. So first of all, so that you start to recognize them and hear the terms. Of course, this is an alcohol. This, when it's a sulfur, it's called a thiol. And when it's a nitrogen with hydrogens on it, it's called an amine. Or biochemistry, we say amino, like for amino acids. And the one down at the bottom, does anyone know what that's called when it's a carbon with 2 oxygens and a hydrogen? It's a carboxylic acid. Okay, so what is the theoretical number? First of all, how many chiral carbons do we have here? We have 3. And so let's figure out, like, first of all, is this one chiral? No, because it's got 2 hydrogens hanging off of it. Is this one chiral, the second one? No, because it's got 2 hydrogens. Is this one chiral? Yes, and so I'm just going to put a little asterisk right there. What about the one below it? Yes. And the one below it? Yes. And the bottom one? No. And the reason why is when you draw, this is a carboxylic acid. This is what it looks like. It only has 3 bonds. It's not tetrahedral. Okay. And so, since there are 3, what's the theoretical possible? The maximum theoretical number of enantiomers? 8, because we have 2 to the n, which is 2 to the 3, which is equal to 8. What's the actual number? Does anyone know? Are there any mesostructures that are possible here? No, so the actual number would be 8. And so that's why if there are no possible mesostructures, there would be 8. Okay. And now, another thing that you can do with this is you can now take compounds and determine whether or not they are identical, enantiomers, diastereomers, that's another possibility, or what I like to call neither, or none of the above, which is where they're just 2 completely different compounds. And so let's do some examples of that. I can get started. If we look at the top 2, we have an alcohol. Technically, we have 2 alcohols. We have an alcohol directly attached to the chiral carbon, a methyl, an amine, and a carbon, a CH2OH, which is technically it's called a methoxy group. It's attached, or methoxyl group. So which one of these is going to have top priority? Which one's going to be the large group. Correct. And why do we know that the nitrogen... Oh, so is it going to be the nitrogen, the oxygen, the carbon, or the carbon? Which one? What's the very first rule? It's the oxygen, because you look at the atomic mass or the atomic number. And so its oxygen is an 8 and nitrogen is a 7. And so that one is the large. So then therefore the medium is going to be the NH2. I'm just going to go ahead and put these over here too as well. Large and medium. And the small group is going to be, yes, an extra small group is methyl. All right, so now we do large, medium to small. And I really don't have much room, so I'm just going to put looks and is like that because there's not a lot of room. So the one that's on the top left, it looks like, does it look like it's an R or does it look like it's an S? It looks like it's an S because it's going counterclockwise. And now the question, is it really an S or is it really an R? Is the extra small group coming towards us or away from us? Towards us, so it really is R. Right? Now let's do the second one. First of all, we know the answer can't be neither because these are, they have the same 4 things hanging off the same carbon. Okay. I used to do that on the quiz. It's kind of tricky, but I used to have this in a quiz where there's like 5 or 6 of these in a row, and I always have one that was neither, where it's 2 completely different compounds, just to see people were paying attention, or I'd have one that another option would be if it was a chiral, like maybe there were 2 hydrogens hanging off, and people would still try to figure it all up. All right, so there's large, medium, and small. We have our looks and is. So is that one, does it look like it's an R or does it look like it's an S? It looks like it's an R. Okay. Now is the extra small group going towards us or away from us? Away. So it really is an R or is it really an S? It really is an R. So now, are these 2 compounds enantiomers or are they identical? These are identical. Even though they look different, they really truly are identical. I'm going to see if it let me scroll everything up. Oh, it won't let me scroll everything up. Okay, so now let's do the bottom ones. All right, so we have a nitrogen, we have 3 carbon containing things, and so which one's going to be the large group? So what's the very first priority? You always go in order of the priority, the rules. The very first rule was you look for what? The atomic mass or atomic number. And so which one's going to have the higher atomic mass or atomic number, nitrogen or carbons? Nitrogen, because its atomic number is 7, its atomic mass is 14. So therefore, it's going to be the large group. The next is, which one's going to be medium? CO2H, CHO, or CH3? The CO2H, that's the carboxylic acid once again. The small group is going to be CHO or CH3? CHO, because that's an aldehyde, by the way. And then this is extra small. I'm going to go ahead and put the same. So we have large, medium. That one's extra small, and that one's small. Okay, now let's do our little swirlies. You always ignore extra small now for the time being. We go to large, medium, small. We have our looks is. Okay, so the one on the left, does it look like it's an R or does it look like it's an S? It looks like it's an R. It's going clockwise. Now we have to say, is the extra small group going towards us or away? Away, so this one really is R or really is S? It really is R. That's supposed to be an R. Now we do the same thing on this other one. So we do large, medium, small. looks and is. Okay. Does it look like it's an S or does it look like it's an R? An S, and is it really an R or is it really an S? It really is an R because it's the external group is coming out towards us. So are these identical or are these going to be enantiomers? Pardon? These are also identical. They're both R's. The only way it would be an enantiomer. Now, if we just took and we switched two of those groups to where we made one an R and one of them an S, then they're enantiomers. But otherwise, they're identical. Okay. I mean, there are questions like that on the exam, just because you have to be able to tell what, if something's an enantiomer, you have to be able to do R versus S. That's pretty much this entire chapter. I didn't ask anything with respect to non-carbon containing chiral centers. It's the same rules. They have to be tetrahedral with 4 different things, and lone pair electrons count. Okay, as being something that's different, but I didn't ask. I don't think there's anything specifically about that on there. Because we don't come across that very often in organic chemistry. You do possibly in biochem, but not in organic chemistry. Okay. All right. So in this example right now, let's first go over and talk about, and give everybody a moment to think this through, how many chiral carbons, if any, are there? So then what would be the maximum theoretical number of enantiomers, if there are any? Okay, so how many chiral carbons are there? There are 3. Okay, we have this one, because it's got 4 different things hanging off of it. Now, if it had just one more carbon going off the other direction, then it wouldn't. Then it would be less, because it wouldn't be chiral, because there would be 2 of the same things, 2 propyl groups hanging off. Okay, we have this one down here, which has 4 different things, and this one. Which, if you had said 4 where you thought that this was a methyl group, I would have given it to you because of the fact that the drawing is poor. Because if that was a methyl group, then that would be an answer as well. All right, and so since there are 3 chiral carbons, what's the theoretical maximum number? 8, because it's 2 to the power 3. Okay. Does this one have any possible mesostructures? No, nothing. I mean, that one, no. I don't see anything that you can have any type of plane of symmetry within this at all. And so you don't have to worry about that. Okay, now let's go ahead and talk about, for example, we could talk about what type of carbons they are. Are they primary, secondary, tertiary, or quaternary? Because I don't think I ever did examples of those in class. They just had them in the book. Okay. So this carbon right here, first of all, what is hanging off of that carbon? 3 hydrogens. Okay, make sure you know how to do that. Like the simple, just know how many hydrogens are hanging off of it. So is this a primary, a secondary, or a tertiary carbon? It's a primary. So that's why, and it's a primary because it's only touching one other carbon. You may ask, and I don't think the book actually explains the whole reason why that's important, is later on when we start doing reactivity, primary, secondary, tertiary, and quaternary carbons have very different reactivities and stabilities. Okay, so that was a primary. The one next to it, is it going to be primary, secondary, tertiary, or quaternary? It's secondary. This one right here would be tertiary, and so that's why it's pretty simple. Now, another thing that we can review, which is from chapter 2, I think, would be orbital hybridization. It doesn't really matter which one you pick, but I'm going to pick this one right here. What's the orbital hybridization around that carbon right there? So I hear sp2. Does everybody agree? Does someone disagree? It's an sp3. How do we know it's an sp3? There are 4 bonds off of it. So remember, what one, you don't want to make any hasty mistakes. What one did you forget? the hydrogen. So if you need to, if it's asking about orbital hybridizations, feel free to draw in hydrogens. That's why I suggest that you do. Whereas if we look at this one down here, what's the orbital hybridization on it? It's also sp3. And this one right here is sp2 because it's got a double bond. Okay? Now you can't make the assumption that all carbons that have double bonds are sp2. Okay, because sometimes people just do that and they look, oh, it's the reason why is I'm going to show you an example of a carbon and a double bond that's not sp2. And I'm drawing all the hydrogens out. Usually, 99.9999% of the time, you can say, oh, if it's got a double bond on it, it's going to be sp2. So this carbon right here, this first one, what's its orbital hybridization? It's sp2. But what about the one in the middle? It's sp, because it's only bound to two things. So it's an s and a p. And that's why, like I said, 99.999, that's probably not the exact number. But most of the time, the vast majority of the time, you can say if it's double bound, it's because it's making a total of 3 bonds. That's something that's sp2. But in this instance right here, which, by the way, this is called a cumulative diene, it's actually sp hybridized. And that becomes important towards the very end of the semester. Talk about hybridization. Oh, I know what we can talk about. And actually use the same big... Let's see. Nope, I want to go back, make this big. Let's talk about shapes and angles. And so if we go back to our good friend here, this carbon, what is the shape around that, the geometry around that carbon right there? It's tetrahedral. And we know it's tetrahedral because 4 things. And so what's the angle around that? Let's say, for example, I'll even be really specific. What's the angle right here? 109.5. Okay? Now, if we look at this one, this carbon down here, what's the shape around it? It's trigonal planar. I'm not even going to attempt to try to write that with my hands because it would get really messy. But it's trigonal planar. It's even hard to say. So if we measure the angle right there, what's its angle going to be? 120, because it's trigonal planar. So actually just that right there, we covered like a good half or more of what we've done all semester long so far. Orbital hybridization, angles, shapes, types of carbons. I wouldn't expect you to know how to name this one because we don't know how to name alkenes yet. Yeah. I would expect you to know how to name this substituent, this functional if you're paying off. Oh, it's one of those tricky ones. Because this gets priority, right? 1, 2, 3, 4, 5, 6. Even though they both got 6, it's the main. Can we get priority? So what would this be called? No, it's not. Whenever it's the functional group hanging off. That's why some of these are tricky. Remember we had like ethyl-methyl, or yeah, methyl-ethyl, not ethyl-methyl, methyl-ethyl groups. What would this one be called? It's an ethyl propyl, and we have to give a locant. And so that's why, and this is one of the trickiest. And the reason why we know that this, you look at the point of attachment. This is the point of attachment. Going one direction, there's 2. That's where the ethyl comes. Going the other direction, there's 1, 2, 3, which is propyl. Remember, don't forget the easy. I shouldn't say easy stuff, but the more simple stuff like meth, eth, prop your butt, pent, hex, hept, oct, non, and dec. Okay, know your numbers because you don't want to miss those kind of points. And so this one is smaller than that one, so that becomes the parent. All right, and so this becomes the functional group hanging off of that. So this entire thing right here, I'm going to type it. Maybe I hate the way that the iPad does this. And so, is it hanging, if off the propyl carbon, for the attachment, this would be carbon number, oh, I misspoke, it's not propyl, it's butyl, because I messed up. Because there's carbon number 1, see? That'd be minus half a point off of Dr. Diastereomers. Okay, it's butyl, there's 4. Okay, because that's what I'm saying, hanging off of carbon number 1 is the ethyl group. It's like, blasphemy. And so, ethyl, but yeah, there's a total number of 4 carbons, because I forgot to count the one that was attached. So then it's a 4. This is butyl. Butyl group. And then that would be like what you would treat that as a functional group of hanging off of whatever it was. So we could have had something like that if we had, instead of that cyclohexane ring, which is what that's called, if that was like a nonane or something, which technically that wouldn't be, or a cyclohexane, that's probably a better one. Then we could have, a 1-ethylbutyl cyclohexane. So, but that's about as difficult as I think that gets. You could have like a 2-ethyl. If that ethyl group, I forgot to hit the OK. If instead, like for example, if this ethyl group was really hanging off here, then it would be a 2-ethylbutyl, because it'd be hanging off the second carbon of the butyl group. Okay.